Okay, so in this video we're going to talk about what makes groundwater move. And actually we're going to talk about two different questions. First, what makes groundwater move, and then how do we know where it's going? As far as what makes it move, it's hydraulic head. So hydraulic head is a measure of the energy in water that is available for flow. And it's abbreviated with this small h here. So in general, water moves from high to low hydraulic head. So the formula for hydraulic head is h, little h equals z plus p. So hydraulic head is measured in meters. Z is the elevation above a reference elevation, and that's usually just sea level, something we're used to thinking about, again in meters. And the pressure head is something typically measured with a piezometer, which we'll talk more about in a couple minutes. Again, measured in meters, so everything is in meters in this case, and this will come up again in a moment, but just remember that pressure head is 0 at the water table, and that's because there's no pressure head. Essentially measures the pressure of overlying water, so at the water table there's really no overlying water, so that pressure is 0. Okay, and this is showing you a picture of a couple of monitoring wells. So monitoring wells are essentially open to water along their entire length. So they're essentially slotted all the way, all through their length, so that water can enter at any point. So the elevation of water in a monitoring well then provides an estimate or a measure of hydraulic head, again h, at the water table. So for these wells, the hydraulic head equals z. And that's because, if you remember, we just talked about P, or the pressure head, equals 0 at the water table because there's no pressure due to overlying water. There is no overlying water. So for both of these monitoring wells, pressure is 0, so the hydraulic head is equal to the elevation of the water in these wells above sea level, or above a reference elevation. In this case, we're just saying that that reference elevation is sea level right here. So Z1 equals H and Z2 equals H2. Okay, so again, water moves from high to low hydraulic head. So what is H, or hydraulic head, for the monitoring wells below, for well 1 and well 2? Okay, you can stop for a moment, pause the video and think about that, or keep going. Well 1, we know that H equals Z plus P, and in both cases for both wells we're just measuring, using monitoring wells, so measuring hydraulic head at the water table, so P is 0. Z for well 1 is 96 meters, so the hydraulic head is equal to 96 plus 0, it's 96 meters. So you can do the same thing for well 2, you can pause and try that on your own if you'd like. So well 2, again, pressure head is 0, elevation above sea level is 99 meters, so the hydraulic head is essentially 99 meters. Okay, so how do we know where groundwater is going? And that's where the hydraulic gradient comes in, and the hydraulic gradient is the change in hydraulic head over distance. So this is what determines direction of flow. So there are a couple different ways that groundwater can flow. It can flow horizontally, sort of flowing downhill across a landscape. So that hydraulic gradient we usually talk about in terms of change in h over change in x, so that's like horizontal space. Something like this, moving downhill from well 1 to well 2, or from well 2 to well 1, sorry. But it can also move vertically, right? So water can be continuing to move downwards as it's infiltrating, or perhaps it can even move upwards towards a river or a lake. And in that case, we talk about the vertical hydraulic gradient. So that's the change in h over the change in elevation between the 2 points within the aquifer or saturated zone that you're interested in determining flow between. And that will become clearer when we do an example. Okay, so the horizontal hydraulic gradient, or change in H over change in X is determined using monitoring wells. So this is essentially following the flow of the water table. So movement between two wells following the hydraulic head, which is essentially the height of the water table above sea level. So, as I mentioned before, a slotted monitoring well will fill to the water table regardless of depth. That is the depth of the well. So again, there's a typo in there, sorry about that. What is P at the water table? It's 0. So hydraulic head for these wells is only going to be equal to the height of the water table above sea level. Okay, so these are just sort of reminding you of the equations. Change in H over change in space, just measured as the height of the water in well 2 minus the height of the water in well 1, divided by the distance between those wells. And I'm again remembering that P is 0. So what is the horizontal hydraulic gradient between wells 1 and 2? So we just take 99 being the hydraulic head of well 2, 96 being the hydraulic head of well 1, which we just determined a few slides ago. Divide that by the distance between these two wells, which is 100 meters. We're assuming everything here is in meters. And you end up with 0.03. So not a hugely strong hydraulic gradient, but nevertheless moving from the higher hydraulic head value to the lower one, from well 2 to well 1. Okay, so a vertical hydraulic gradient is determined using piezometers. So piezometers provide a measure of hydraulic head at the slotted end of the well. So piezometers are only slotted typically at the end of the well. Oops. So that's kind of what this picture is showing you here. A bunch of different piezometers, 3 different ones, and you can see that we're no longer just measuring the hydraulic head at the water table. Now we're measuring it here at this slotted end, so you can see the pressure is elevating the water in this particular well. And then here we're measuring hydraulic head at this slotted end, and here we're measuring it at this slotted end. So you can see sort of the impact that the overlying pressure of the water has in these wells. Okay, so just a little bit about piezometers. So this is showing you a monitoring well here. It's slotted all the way down so water can enter anywhere. Piezometers are only slotted at the bottom of the well, so this is the only place that water can enter. So that the hydraulic head, H, is measured only at this slotted portion of the piezometer. So the elevation of the water in the well tells you the hydraulic head at the slotted section of the well. Okay, and hopefully this will become a little bit clearer as we continue on. Okay, again, piezometer only slotted over a small vertical distance. It measures the hydraulic head at that point, and the elevation of the water in the well is the hydraulic head at the slotted section of the well. Okay, and here is an example of what that might look like. So how do you measure the vertical hydraulic gradient? Again, you need piezometers. So in this case, P is no longer 0 because we're measuring, these little dotted areas are supposed to show you that the wells are slotted down here. So we're measuring hydraulic head at these areas within the water table because the water table is here. So we're measuring it here. So you've got overlying water. So there is pressure being applied due to overlying water at both of these points. So now H is equal to Z, the height of the slotted section of the well, and P. Okay, so we'll show you what that looks like here in a second. So here's our reference elevation. In this case, again, we're just going to assume that this is sea level. So Z for both of these wells is the height of the slotted section of the well above that reference elevation. And P is the distance between the bottom of the well and the height of the water in the well. Okay, and both of those things added together give you H. So in practice, really just knowing the height of the water in your well above sea level is all you need to know. I'm just showing you how that gets broken down into Z and P in this case, but they add up to the height of the water in the well above sea level. So in this case you can see for well 1 we've got a lower hydraulic head than for well 2, and we can put all those values into the equation, get a value for the hydraulic gradient a bit higher than the one we had before. And just remember that the flow is down from well 2 to well 1 because this hydraulic head is higher, and flow is from high to low hydraulic head. So we're moving from this point in the water saturated zone to this point downwards. Okay, so here's your sort of sum up. For hydraulic gradient, horizontal flow follows the water table, essentially with hydraulic head being equal to the height of the water table above sea level, and it's measured by monitoring well. And then vertical flow follows changes in Z and P, and it's measured by a piezometer. So water in general moves from high to low hydraulic head, horizontal water movements estimated by the water table height, and vertical water movement is estimated using piezometers. Okay, and then we can show groundwater movement using flow nets, and that's what the next video is going to talk about.